Okay, hello everyone. I am Brenda Huppenthal. I am a graduate student with the Data Science Institute, and here today I'm going to be teaching you guys the basics of using scikit-learning with a pretty large variety of different machine learning tasks. So I'm aware that because this is the data science workshop series, that probably a lot of this material could be new to you. The different models and things could be new. So really what I'm hoping that you take away from this session is just an overview of what kind of tasks are out there that machine learning algorithms can solve. Some basic ideas about how you would use scikit-learn to solve those, but more importantly, a lot of code examples that you can take away and start to play with and test around, like play around with and test in your own time. So let's go ahead and get started with that. And also, if in the chat you have any problems hearing me or you can't see the screen, just let me know. Yeah, Carlos, can you? Okay. Okay. So a brief look at the machine learning landscape. I guess I'd be curious to see, for those of you who are here online, what kind of experience you have in this area. I don't know how many people are here from our machine learning series that we're also doing. So if you want to post your replies in chat, that would be helpful. Otherwise, I'll just get straight into it. So machine learning, the purpose of machine learning algorithms are basically to take in some sort of set of data and allow us to make useful predictions based on those. So there's a bunch of different kind of areas of machine learning. So there are machine learning algorithms that actually don't have anything to do with artificial intelligence, that are purely math driven. They're not updated via a learning process or doing things like what artificial intelligence is doing with neural networks or AI. And some of the tasks that we have and that we can use machine learning models to solve are many computer vision tasks. Probably the most interesting and easy to grasp, like just right off the bat, would be object recognition, where you have some picture or you have some video, and what you would like to do is just automatically identify, first of all, here is where the object of interest is. So I want to generate some sort of bounding box around, for instance, like my face or other objects of interest. And then that leads really easily into doing tracking, which is, okay, now we have some video, which is just a series of still images, and we have these bounding boxes, but we need to figure out some sort of correspondence between this frame to this frame. Where is the object moving to? You can also perform tasks like automatic summarization, which would be an example of a natural learning processing task, where what you're trying to do is just feed in this full document and have it give you just a couple sentence summary of the most relevant information from it. We also care a lot about, like at a very high level, prediction tasks, which would be, we have a bunch of historical data, and given some new features for a data point, for example, like I have all of this information about houses that have sold in my neighborhood. So I have information about their square footage, things of that nature. And then I want to predict, okay, based on all of these sell prices, what do I think my house is going to sell for? Classification is somewhat similar, except that now instead of having some real valued output, so like a price of a house is a real value, instead what we're attempting to do is say, okay, based on these features about this data point, here's the class that I think it falls into. So if we had real features like, okay, I have this pet's weight, maybe the color of the pet, some other different things you could label and measure about it, then you can say, okay, I think it's a cat, a dog, a lizard. You're assigning some sort of discrete label to it. Clustering is another thing we can do where we try to take data points, and we may not have labels that are meaningful for these, but we want to try and cluster them in some way that is meaningful. Typically, you'll see this in like, maybe you have some sort of information about users and you need to come up with 2 or 3 categories of users where the users behave in similar ways across the category. So clustering, classification, and prediction, we're going to see all of these examples with the Scikit-Learn workshop workbooks that I will show you. But But things like automatic summarization, object recognition get a little bit too complicated for what we'll be looking into today. And then the last one would be recommender systems, which is generally, okay, you looked at this, this, and this on like Amazon, you clicked through these links, and now we're going to try to figure out other people who also clicked on similar links, what did they go on to look at? And we're going to try and recommend you something similar. So you may recognize if you've been looking at a bunch of like vacuums recently, and now all Amazon thinks you want to look at is more pictures of vacuums. That would be one thing that's coming out of a recommender system. Then a really high level like history of machine learning. This focuses a little bit more on like the origin of deep learning, more so than machine learning as a larger field. But 1943, you have McCulloch and Pitts writing a paper about how neurons work, which eventually becomes the very basic building block in what we now call neural networks. So first, we're just looking at and trying to understand how the brain is working. In 1950, Turing comes up with this idea of the Turing test, which is one measure of intelligence for some sort of system would be if in conversing or interacting with that system, you cannot tell the difference. You cannot tell that it is a robot versus a human participant on the other side of the conversation. We have computing also starting to emerge at this time. Turing is also very important in this field. And then by 1957, we have taken this idea of neurons and started to build neural networks, which can be used for like the first thing they were used for was classification of just handwritten digits. We have another very famous algorithm coming up this time called the nearest neighbor algorithm, which can be used for clustering. We'll definitely see this one. By 97, we have Deep Blue, which is just a chess program that could beat the world champion at the time. And then by the time we get to 2006, we started moving just from like single layer, a couple layer neural networks into deep neural networks that are driving what you think of as like ChatGPT, things like that. That is when we start to like really look at, okay, we can throw a massive amount of computing power at this problem now. So let's just make these really deep neural networks and see what kind of things they can learn. But that's just a really high level view. We're not going to be doing too much of that today. We're just going to be looking at Scikit-Learn. So quickly, I believe that you guys have been looking at, for example, the like scientific Python computing libraries, and Scikit-Learn slots very well in with all of those. So as you've been working with NumPy, Scikit-Learn is built basically directly on top of that because NumPy is so good for scientific computing applications due to the speed and the fact that many of these computations are parallelizable. So first thing, I just want to take a look at some of the documentation. We'll be taking a couple of trips into the documentation just because I think it's a useful skill to be able to learn. And then also just by looking at this, it'll give you a starting point and okay, we didn't cover XYZ algorithm that I would have wanted to cover. You can come here and see what they support. So here, this is just like, it's a massive page. I'm not going to scroll down all of it, but you can see that they kind of have it organized by topic. So calibration, classification, like if, for example, I was like saying, okay, I want to do a linear discriminant analysis, I can come here and then they just actually give you code snippets for generating the data, performing the analysis, and plotting it as well as I believe they should have an example. Yeah, so they'll show you also the example output that this code would give you. So it's a really good starting point if you want to do this. Just take this code and kind of tweak it until it works with the specific data set that you're working on. And then if we go back, we can see like, okay, they also support neural networks. Just you can come in here and kind of poke around and see like along the side everything that they cover. Okay. One thing with Scikit-Learn, so they do support a massive number of machine learning algorithms, but they don't support really like in-depth neural networks. So if you're looking to play and change like neural network architectures as you're doing development, I wouldn't recommend using Scikit-Learn for that. I would recommend using like PyTorch or TensorFlow, which are significantly more flexible. Scikit-Learn basically just lets you define like a couple layers, the number of neurons per layer, but it doesn't let you do more advanced things. And then if you're also interested in the computer vision space, they have Scikit-Image as well, but we won't look at that today. And also our examples today, they're going to just use data sets that are like just toy data sets. And Scikit-Learn actually provides a lot of these for you just in their library. So if we want to take a look at, okay, I want to maybe learn about how to do this, but I don't have a data set yet in mind. You can come and just see, okay, let's look at what kind of data sets they have. So like, I think the iris plants data set is very famous, but they have a decent number that you can pick between and play with as well. Okay. So classical machine learning algorithms, a very high level overview. We have supervised and unsupervised learning. So in supervised learning, we have some data point, X that's got maybe 3 different features. And then for that data point, some information about it. So you either know that this data point maps onto this function value. So like our house example is we have some data about the house and it maps onto a price. Whereas in unsupervised learning, some information about this, but you don't necessarily have a label from it. So that would be the example where we want to group users in some sort of meaningful way. So we have information about the users, but we don't have any sort of a priori knowledge about a label for them. And then so supervised learning, because you have these labels, that's like regression and classification fit in there. Yes? Sorry, no question. So classification, anything again that you were just saying, we want to put you into a class. One example would be k nearest neighbors. You can use it to do classification. You can use decision trees, which basically for every query point, you would say, hey, for this one feature, is it greater than or less than this value? Is this true or is this not true? And you just keep asking questions until you kind of get down to a point where you say, okay, I'm confident enough to assign this class. There's very, very many different things that you can use. And we can see that some of these we've just posted in here links to specifically the Scikit-Learn page that covers it, which also will give you some of the example code for using it. And then for prediction, similarly, like linear regression, I think very many people are familiar with polynomial regression, logistic, et cetera. So that's getting your real value out of your data points. And then here quickly, we have evaluation metrics for those. So this would be useful these are useful for classifiers, and essentially these are all metrics that use 4 underlying cases that you can have. The 4 underlying cases being, okay, my classifier said that this is class 1, and the true value for it is class 1. So that's a true positive. The classifier and the true class agree. You can have a false negative, which is, okay, this is class 1, but it said it's class 0. So it set a negative value, but it's incorrect that it was negative. It was actually a 1. And then the opposite for false positive. It said that it was 1, but it's actually 0. And true negative would be it correctly predicted that it is class 0. So they're just a couple different metrics here that kind of evaluate, okay, how many of these values did we get versus how many should we have gotten? So how many true positives do we get out of everything that it thought was positive, et cetera. And then for regression, you have things that are just like mean squared error, or you take the absolute difference between, okay, I predicted 7, it's actually 6, the error there is 1. So let's jump into specifically this ML classification workbook. Actually, let me see if the link is still. Actually, I'm going to share this link in the chat. I believe yeah, it's this one. Okay, so I just shared the link to this workbook in the chat. This is going to be a workbook where we work through just okay, maybe not. Sorry, 1 second. Classification. Okay. I'm just gonna download it, upload it, and then I can change that link. Oh, okay, I see. Okay, thank you. Okay, sorry about that. Not sure why that did not show up there. Okay. So if you're having any problems opening it directly from the Colab notebook, just go ahead and go to Colab and then have it open from that link like I just did. So we can fly through this pretty quickly. What we're going to be doing here is we're actually going to be using the iris data set. So this is a data set where we have flowers. We have different measurements that were taken off of flowers, and the output, or what we're trying to classify them into one of three different species. So we can see that like some of the attributes that we have are I believe it's sepal length and sepal width, as well as petal length and petal width. And then of the classes, we have Setosa, versicolor, and Virginica. So we just want to train some sort of model that, given access only to this information, can predict a class, so that once we've trained it on all this data, we have a test one that we're not sure about, and it will give us the class for that. So here, this is just doing a little bit of work with the pandas data frame. So it's just printing out, okay, what are the target names, feature names, etc. Not super exciting. And here, all we're doing is just printing out, okay, the first 5 rows tell me what the features are for those 5 flowers. And you can see from this here that we have 150 examples of these, and it's 50 each of our 3 classes. So the first thing with all of these machine learning models is we want to make sure that when we are training our models, we want to split this into a train and test split. So we have some amount of the information that's going to be in the training data set. We train the entire model on that, but then we test it on this held out data that it's never seen. One thing that can happen with a lot of machine learning models is if you are testing on points that it's seen in the training data set, it can just memorize exactly the answer to that, and then it's not actually going to tell you the accuracy on that test data set if it's already seen it. It's not a good representative of how it's going to perform on data that it has truly never seen before. So here, Scikit-Learn just offers you a function that's going to split these. And we're going to say, okay, we want the test set size to be 30% of our entire data. And then I believe this just randomizes it so that you can shuffle the data set before you pull out the 30% that's going to be the test. So now we have these split up into features, test, features, train, and then labels, test, and train. And we can see that 30%, so it pulls off 45 of these for test examples, and the remaining 105 will be used for training. Let's see. I'm actually going to remove this. Okay, never mind. Okay, so the first thing we're going to do is with pandas, specifically, we're just going to look at a scatter matrix. This is an exploratory data analysis first step that you should take when you're working with data. So you can see that, okay, along this scatter matrix on the diagonal, it's just, you would be comparing the feature to itself. So it's just giving a histogram of, okay, for our sepal lengths, how many of each do we have binned up? And then for these off diagonals, what it's going to do is show the sepal length plotted against a second feature. So I'll show this one. This would be petal width against sepal length. So you can kind of see that, okay, for this one class, there's a very strong, like they are both very small together. So this class does not have very large sepal lengths associated with large petal widths, etc., which can help you sometimes if you're trying to choose an appropriate model. So the first model we're going to look at is k-nearest neighbors. And all k-nearest neighbors is going to do is say, okay, I have all of my training data. So whenever I put a new point in here, I'm just going to look at the closest k points, and I'm going to ask them, what's your label? And then the most frequent label that I get out of all my neighbors, that's just what I say that I am. So like, for example, if I put a point like right here and I say, okay, what is my label? I'm going to look at the 3 nearest ones. Well, maybe it's like this point, and this point, and they are all in agreement. We're just the blue class. So that's why I would put out. So Scikit-Learn helps do this by just giving us a k-nearest neighbors classifier, which we're importing. And then what you first need to do is say, okay, I want an object of this class. So that's what this line is doing. We say, okay, our little KNN object is just this classifier. And we set it to say, okay, I only want to look at the closest point to me. So the number of neighbors to look at is just one. So with that set up, we fit using this training data. So now we say, okay, use this data when you're doing these query points for the test points. So here we just make that new point and then ask it to predict for this new point. So this prediction is performing that process of look up the closest point and give me back the class of that closest point. So we can see that it was closest to one of the Setosa flowers. And then here we're just running it on the entire test set for the predictions. And then here we're looking at, here's the accuracy. So how many of these had the predictions exactly equal to the test classes. And then Scikit-Learn is also going to give you a confusion matrix. So here we're just checking of the class, of my true class, how many of them were correctly predicted. So that's going to be on the diagonal. This thinks the classifier said it was class 0, and it was actually class 0. The off diagonals would say, okay, the classifier thought that it was class 1, but truly it was class 2. This can be helpful if you're just looking at, okay, if I'm having a pretty large accuracy problem, is it mostly confusing specific classes with one another? So you can see that it has some confusion between classes 2 and 3, but it's very, very good at classes 1 and 2, but it's very good at classifying class 0. And then we can get a heat map, which is similar. I think it's just using it looks like it's just using the percentages of, okay, 16 out of our total number of samples, etc. We can also have Scikit-Learn just calculate all of the different metrics that we were talking about earlier as well. So here we import this function called classification report, and then just pass it the test values and the predicted values. So it will give us precision and recall, which are both, I believe it's false negative and false positive, but I'm not 100% sure, as well as the F1 score and support. And then here, this is just one block where we take all of that together and put it in one, just so you can see it's really not that much code required to implement this entire process. Okay, so we're going to look at a second classifier now and talk a little bit more about some more things that we can do with them. So for hyperparameters, I don't know if anybody here, are you familiar with what a hyperparameter of a machine learning model is? Okay. Doesn't sound like it. All right. So a hyperparameter here would be, in our k-nearest neighbors example, the hyperparameter is how many neighbors do I look at? So it's just something you can tweak in the model that is probably going to change the model performance, accuracy, things like that. If you start to look at more and more neighbors, that might be helpful in some instances, because let's say that you end up querying a point right here. You can see that if you look at just a single neighbor, you're going to get it will spit out this orange class. And then the more neighbors you look at, maybe you pick up this one and this one, and it's still telling you orange. But if you continue to search out further, it could change the amount that it's picking up from both of these classes that are really close together. And typically, for example, you wouldn't want to use just one, because if I end up hitting a point that's right here, I would probably say this should be green, because you just have this one orange point that's kind of out away from the main cluster. But if you look at only one neighbor, it's going to tell you that it's orange. And then a very silly example would be if I look at every single neighbor, it's always just going to tell you what the maximum, the class that has the most instances in your entire test set is. So that's something you can do that's going to change the model performance, and you kind of want to hit a sweet spot of how many that you look at. So one thing that you can do is you can train a couple of different of the same type of classifier, but all you're doing is you're just changing that hyperparameter, and then you pick the one that's going to give you the highest accuracy on your test set. So that's what we're talking about when we talk about hyperparameter tuning. And then cross-validation is similar. Cross-validation is if you just have a single train and test split, you will just get one number for the accuracy. But you can imagine that if you're changing the data points, like which ones end up in train and which one ends up in test, could also impact the accuracy that you're getting. So all cross-validation is doing is it's saying, well, every time I train this, I'm just going to split this up in a different way. And then I'm going to help let that inform me of whether or not this is a good model or not. It could be that you get a really poor accuracy because you just have like one really horrible train test split, and cross-validation is a way to protect against doing that. Okay, so decision trees, let me see what this is. Okay. Okay, so this would be just like a quick example of what a decision tree looks like. We have passengers on the Titanic, and we are just for every passenger, we have some information, obviously gender, age, whether or not they survived. And we are asking them, okay, for you, what is your gender? And then if they are male, we would say, okay, the next most informative feature that's going to tell us whether or not you died or survived is what your age was. So we can continue querying the data until you get down to just this base level, at which point we are confident enough to give you a class. So the things that you would be able to change there, let's see here. You can essentially tell it, so we're looking at a couple of the hyperparameters here. So the hyperparameters for a decision tree would be, okay, how many questions am I going to let it ask this data point? A very, very shallow decision tree would be, okay, if you are given a single question, you can only ask one question, then you have to say, this is class A or this is class B, you know, died or survived. In this case, it would be which flower are you? So you would basically be able to say, okay, I have to figure out what the most important feature is, and I can only ask based on that one to get one of my three classes out of it. But then the larger your decision tree gets, the more questions you can start asking. And then you can essentially start asking too many questions where you're overfitting your training data, and you've just found like one data point where maybe this was very informative for the data points. You ask that question, but it doesn't work for most of the other data points. So you're overfitting the training data at the expense of accuracy on the test data set. So that's what we're trying to do here. We're just trying to say, okay, we have all these different hyperparameters. We have a bunch of different settings. And what we're going to do is we're going to just try all of them together in this quote unquote hyperparameter grid search. So you just make a grid and you're going to try every combination of these. And then it's going to handle the search for you, train all of these models, and then return the one that was giving the highest accuracy on the test set. Okay, so we're splitting it here. We define this dictionary that's going to tell it, okay, for all these features, here's the values that I want you to try for the hyperparameters. We create the decision tree classifier, and then we do this randomized search. So we pass it in the tree, we tell it what hyperparameters we want it to try, and then we're going to fit this to our training data. Okay, so this tree CV, this random search, we can see, okay, this is going to, if we access this attribute here, it gives us the best parameters back out of it, and then the best score as well. And then you can also just, again, this tree CV, we're going to use it to predict on our test data point and get all of these Y predictions out. And then you can, again, do the confusion matrix and everything else that you would normally do to check your classifier. So we can see that trying all of these things, their decision tree parameters were, it gives us this max depth of 3. It's going to use 6 of the features, and it's looking at just everything that we put in here. And then from that, we got a 97% accuracy from that best tree. Okay. And then similarly, just a really quick example, you can also do logistic regression classification. So just using iris again, very little is changing here. The parameter grid, all we're changing is this constant that's kind of regularizing it. And then specifically the penalty that we're using, which is just saying for all of the coefficients that it's fitting to our regression, don't make the weights too large. And there's a couple of different ways you can do that. So we're penalizing it in two separate ways. Here, we're using the logistic regression class with specifically this solver and max number of iterations. We're just giving it a max number of iterations to say, like, you can stop training after this point. I think it will stop before that point if it's not seeing any improvements in the accuracy. But yeah, it's very similar in that, like, we instantiate the class, we make this grid search, and then we're going to do this fit, where we use the grid search to fit this training data, and it's taking in the specific classification model here. Again, just looking at all of these best parameters and then the heat map as well. So this one's doing quite well. It's only wrong for two of the examples in our training set. And then this is an elastic net regularization, just another type of classifier where it's mostly the same. Here, what I had to do, when you're running machine learning models, typically what you would like to do is you need to standardize the input data. So you can have an input data, let's say that it's normally distributed. So you have some mean, like if the mean is like 10, 10, and you have some variance, so it's really spread out. So you have all this data and it's just kind of like up here in the positive XY plane area in this quadrant. And it can help basically to take all of that and then shift it down. So down, the mean is now at 0 and the variance of that data is 1. So the weights and the weights and everything that the machine learning classifier has to learn can be smaller as well. It can essentially just smooth out the training process to do this this scale and shift. So because it's so useful, Scikit-Learn provides that as a specific feature, function as well. So here, this is we're getting it imported from the pre-processing module. It's pre-processing because it's something that you need to do to your data before it gets fed into the classifier at all. Standard scalar. So then here, again, Scikit-Learn is object-oriented, so we need to instantiate this one version of this class. So we get this scalar, and then we tell it, okay, fit on our training data. And all this is doing is it's saying, okay, for this training data, here's what the mean is, the center of all of this data, and then the variance. So now when we actually call this elastic net to fit on our data, instead of passing in xtrain, we're going to apply the scaling to it. And that's all this does. It's saying, okay, take this X data and then transform it by the mean and the variance that you learned. And then we're going to fit using that instead. And then anywhere else where you're using it, it would not work. So if you just did the training data and then you did not scale the test data, these two could be very, very far apart in terms of the actual values of your test and your trained data. So when you're using it for inference and prediction, you also need to transform all of the feature values that you're feeding in here as well. So that's why we're doing the transform on the test data. Okay. And then stepping back from that, you might have noticed that we're doing a lot of the same things kind of over and over. So Scikit-Learn can provide, it provides this functionality called pipeline. And what pipeline is going to do for you is essentially, it'll just take all of this code that we're trying to use and it's just organizing it into steps. So here we're back to a KNN, but what we're doing, the K nearest neighbors classifier. But what we're doing is we're saying, okay, now we want to add this scaling. So we're going to take everything, shift the mean down to 0, bring the variance into 1, and then we're going to apply the K nearest neighbors classifier on that. So that's what the pipeline is going to let us do. We basically say, okay, here are the steps that I want you to take every time you get a data point. You're going to scale it, and then you're going to feed it into this K nearest neighbors classifier. So we just say, okay, this is the list of the steps that we want, where we have this tuple of name of the step, and then what the actual object that you're going to apply to it is going to be. And then we give that list to pipeline. So now what pipeline is going to do is everything that you give it, it puts it through those in order. So when we're doing this pipeline.fit, it takes this X train data, scales it, and then fits the k nearest neighbors classifier to it. And for the prediction, it takes the X test, scales it, and then gives you the predicted values out of that trained k nearest neighbors. So that's just one thing you can do that's going to make your code a little bit easier, rather than having, okay, scalar, and then I need to do the transforms for everything. It just sort of wraps that functionality up and makes your code a little bit simpler to read. So you can see here that there's not a difference in, so for this, the k nearest neighbors, the scaling does not help with the accuracy, but it will help with accuracy and also convergence times for other algorithms. Okay, and then a slightly more complicated example. I think it said that it was going to do that. Okay, so here you can see it's the previous example where we're using this pipeline to do the scaling in the k nearest neighbors classifier. And then you can actually pass this pipeline, which is going to do those two steps, into our hyperparameter grid search. So we give it the pipeline, and then we're also going to still give it the grid. So now the grid search is going to be able to do all of the scaling and also be able to pick all of the new hyperparameter combinations out of this grid and test all of them together. And this basically just replaces like a for loop that would be doing that for you. Okay. This example, I think we can skip for the purpose of time. I will just point out this is kind of a nice example of like what KNN is actually doing. So here we have, I am looking up this test point, and then the closest point is this one. So you can see that's why it's grabbing blue here. Versus, okay, now we're looking at 3 neighbors. So we grab this blue point, but then these 2 orange points. Not super exciting. And then one other thing you can look at, this does not specifically use Scikit-Learn, but it uses this library called mglearn, which is, I think, a pretty small library that's just used for, I believe a professor developed it as a pedagogical tool to show what's happening in some of these examples. But here we're just taking a look at our k nearest neighbors classifier, and we want to see the exact boundary at which you switch from one class to another. So you can see that like this is where that boundary would be. If you're on this side of the boundary, you're getting the orange class versus on this side, you're getting the blue class. And you can watch how this is actually changing as you're increasing the number of neighbors. So with only one neighbor, as expected, this boundary is really jagged because it's being influenced by a single point. Versus the more neighbors that you start to look at, it smooths the boundary out and you're not overfitting to these points, which are arguably on the wrong side of the boundary. So they just have some noise or something included. And this is an example of, okay, the hyperparameter search that we've been letting Scikit-Learn handle for us. Well, if you don't want to do that and you want to actually just write out the for loop, this is what you would do. So you just have this list of, I want to check all of the neighbors between 1 and 10. So you just make that range. And then for every single number in that range, you're here just manually making another nearest neighbors classifier, fitting it, and then calculating the accuracy and appending it. So this is what essentially the grid parameter search and all of those hyperparameter searches we were looking at, they're doing this under the hood. But if you want to take a look at this to have a better idea of what they're doing, this is exactly what they're doing. And then that also is just giving us access to, okay, we can look at how the training and test accuracy are changing as you're increasing the number of neighbors. So the test accuracy actually is the smallest it can be at 2 and then bounces back up again. Okay, and then this, I don't believe we need to discuss this again. It's logistic regression. Yes, I think we're okay not to talk about these ones. The decision tree we discussed as well. Oh, this is a nice example of, so for the decision tree, you have all of these different points, and what the decision tree is doing, because it's asking these yes/no questions, the more yes/no questions you let it ask, it can only make these linear boundaries, but they can still start to get much more complicated as you add these linear boundaries together. So here you're just saying, okay, if we can ask one question, this is where our best split would be between these two classes. If we're given a second question, so now down here, I can ask this second question. We can take these 2 points and correctly classify them. And similarly, up here, a second question allows me to correctly classify these points. And then arguably, again, this would be an example of your machine learning model overfitting, because you're starting to carve out these really small regions in the middle of like this very nice cluster of blue points. So it's sort of making it's overfitting your training data, and a test point you would actually expect would probably be blue if it was landing in here. And then this is, yeah. So that's the end of this this part of the workshop. Is that out? Okay, so in the second part, we're going to talk about, we just talked about and looked at the code for a lot of supervised machine learning algorithms, which again, assume that you have some sort of output for your point. So you have all of these getting collapsed through a function to give you some real value, or you get some class or things like that. Here, what we have is just all of this data, which has some number of features, but it doesn't have some sort of output or label associated with it. So one example of why you might be interested in data like this is dimensionality reduction, where maybe you have a bunch of data points that you've taken, and you're curious, okay, it has this like interesting structure, but I'm more interested to see, rather than having it in this high dimensional space, can I get that down to just 1 or 2 components that tell me most of what is going on here? So dimensionality reduction is really useful for, like, we have some data point where there's like 50 different things that you can know about. It has 50 features, and we're mostly curious, okay, but are any of these covariing, and can we distill that down into just 2 or 3 features of interest? Because if you can do that, typically you could take like a dimensionality reduction algorithm, run that on your data first, and then run some other algorithm on it after the fact on this like much smaller data set. And that is helpful for a lot of reasons, one of which it's computationally generally very nice to run these algorithms on things that have very small dimension. As the dimension starts to increase, you have to invert matrices and things like that, and that is a very like it's an expensive operation if you have a lot of features of your data. So principal component analysis is probably the most well-known dimensionality reduction algorithm, but it's certainly not the only one. They all operate in different ways that are just trying to actually capture what is driving the variance, which of these are co-varying together, and can I just collapse that down into just one simple factor for this. Another thing, I don't really know anything about association rule learning, but if you have a bunch of data and you just need to try and figure out why various pieces in this data are connected, like what rules would, by learning those rules, you'd be able to understand some sort of underlying relationships in your data. And then clustering, this would be if we talked about like various users trying to figure out, okay, are there maybe 3 groups of users and I can like target my content towards them in different ways. Clustering would be one way to do that. So I think clustering, the easiest one would be k-means, where you're just trying to figure out centroids for some clusters. So you say, okay, I want to make this into, if you see this data, you could say, okay, I want to make this into 2 clusters. Maybe you think that you don't need to cut this one up. So you'd say just a priori, I want 2, and it will give you this one and this one. Or I want 3, and it cuts it up in this way. And you can just continue to throw means at it until you get down to 1 mean per point, which is obviously not very helpful in the realm of clustering. But that's only one way of going about doing this. There are a lot of different clustering algorithms as well. Let's see, we do have this notebook for the dimensionality reduction and clustering. And hopefully this one works, but if not, okay. Okay, so in this data set, we're going to be using the penguins data set instead of the iris data set. The idea is very, very similar, where we have penguins that have some categorical features, some real valued features. So the categorical being what island is it from? The real valued being like what's the weight? And in this instance, we do have, you could treat this as a classification task by trying to predict, for example, the species based on all these other ones. But we're going to instead pretend that we don't have that information and just try and figure out, okay, I have XYZ real features. Let's try and figure out meaningful, semantically meaningful groups of them. So this is mostly pandas things as well, and we can look at the pair plots again. Here we're using it with Seaborn instead of, I forget what we used for the previous example. So one thing we can do with this data set is say, okay, we have these, I believe it is 4 real valued features. You have Coleman length, Coleman depth, which is like beak length and height, and then flipper length and body mass. But you would expect that these would be varying together. Like a penguin that has higher body mass should also have like a longer beak, a taller beak, just like longer flippers. So you would expect that maybe there's only 1 or 2 different principal components that we could use, or we could reduce the dimension, and it's still going to capture all of the variation here. So we are just going to do that with, let's see. So one way you can actually measure this is with the variance inflation factor, which here we're just using to get, we're getting this with NumPy rather than going through Scikit-Learn. Because again, like Scikit-Learn is built on top of NumPy, so we can do that very easily. For the principal component analysis, you'll notice here that we also are using the standard scaler. And Scikit-Learn provides principal component analysis just as another class that you can use on this data set. So we make our little instance of the class. And here what we're doing is we've previously seen the 2 separate methods, fit and transform. So what fit underscore transform does is it does both of those at the same time. So it's going to fit to our data, and then it's also going to transform our data into these principal components. And for the principal components, you can actually see, okay, the 0th principal component is going to take our data and turn it into like this value. So along that first axis, this would be the first value for that, and so on for all of the principal components. It'll also give you the eigenvalues for the covariance matrix, which is how you calculate this, but I'll let you look that up if you're interested in understanding the underlying theory. We can also get to, once you've calculated these principal components, the important thing would be, okay, well, did this gain me anything? Are all of these, like this first component, is it actually capturing more information than just any of the individual features themselves were? So we can get at that with this explained variance ratio attribute. So you can see in our PCA that we've fit, we're telling it, okay, you already fit this data, so give this information to us. And it'll tell you that, okay, our first principal component is actually, it can explain 70% of all of the explainable variance in this data set. So we're capturing a lot of information using just a single number. We would be only losing 30% of the explained variance if we used a single number instead of these 4 numbers. The second one gives you another 20%. So if you were to use only the first 2, you can get all the way up to, what's it, 90%-ish. And that's all this one is showing here. We're looking at, okay, for our explained variance, as I'm increasing the number of features, so as I'm marching through my principal components, how much of the variance am I explaining? And then this is showing us, okay, the principal components, what are they actually made of? Because they're just linear combinations of all of the features that we already had. So it'll show you principal component 1 is, would be this number times the Coleman length, this number times the Coleman depth, etc. And that's how you would actually calculate this principal component. So a really small value would be, okay, principal component 2 does not depend at all on the flipper length. Or really on the body mass. It is entirely on the beak size. And then these are just plotting feature importance, which is, so if we take all of this information and then we'd say, okay, the linear combination, here's the size of how much this is contributing to this second principal component. Okay, let me just double check. So this is a lot of graphing. It doesn't have anything to do with Scikit-Learn. We'll just look at one more example and then I'll take any questions before we end here. So linear discriminant analysis would be another way that we can do clustering or excuse me, dimensionality reduction, which might be helpful for clustering or for classification as well. So here, similarly, again, we just use the standard scalar, and then we're just doing a PCA here to compare it to, but instead of using PCA, we use this linear discriminant analysis. And in this instance, you can tell PCA ahead of time, I only care about the number of components, and linear discriminant analysis as well as basically saying, okay, I want you to take this and then fit it, and you can use it most 2 components here. And you can change the solver as well. That's what it's doing in the background to come up with the components. I would recommend for all of these, like, just go look at the Scikit-Learn documentation because they will tell you a bit of information about the solvers. For some cases, like if you have a really sparse matrix, like one solver may just not be able to deal with that, whereas another solver can. But for data that does not have that, the first solver is significantly faster. So you can play with essentially how much computation is required for fitting these models. And then here's just a really simple, now that we've done this decomposition from this 4-dimensional space down to this 2-dimensional space, let's take a look at these different clusters in this reduced space. So you can see the linear dimension analysis is doing a better job of separating the different classes than the PCA can. Okay, I just want to make sure that I didn't miss anything that I wanted to talk about. Reinforcement learning, this is further into the artificial intelligence space, but this is essentially how you train agents to interact with the world. So it's a very big part of artificial intelligence, but I don't think we have enough time to go into it here. And then ensemble learning would be, okay, maybe we actually don't just take only the best classifier. Maybe we can train a couple of different classifiers. So for example, like 3 or 5 decision trees that all split on different features. So they're all trained differently. But then we're just going to run all of these classifiers on our data point and have them vote on what the correct answer should be for it. And that's pretty similar to what bootstrap aggregating and bagging are doing.